Good afternoon, everyone. Today is lecture number 27 of this heat treatment class, and today's menus are basically on hardenability concept. So, what is hardness and hardenability? What is the difference? And how to get maximum hardness in plain carbon steel? So, when we have only carbon in the steel, how we get maximum hardness? And third one is condition affecting the hardenability of steel. So as you remember, hardenability is a very important properties of the steel and whereby which we can harden a steel. So what are the properties that affects them? We'll discuss it in a details in coming lecture, but today I'll tell you just an overview of that. How to get martensite at the core center of the specimen and what is the consequence of this. So if you remember in the previous lecture, you have seen that the cooling rate is faster at the surface but slower at the center, right? So in that condition, what happens basically? Due to different cooling rate, at the surface the martensite will form, and at the core or at the center, perlite will form basically. Then steel types on the basis of hardenability. So on the basis of hardenability, we can have different type of steels. We'll discuss that. And ways to distinguish perlite and martensite microstructure in the steel. So suppose in your steel you have different microstructure at different cross section, right? Like from at the surface you'll be having martensite, and at the core you'll be having perlite. So how to distinguish them, or how to identify the microstructure, or how to distinguish the martensite and perlite. And last one is significance of hardenability. So what is the significance of hardenability? And also we have a lot of topics we'll discuss today. So before starting the lecture, let me recall what is hardenability again. So hardenability is the susceptibility of a steel to harden, open, quenching, right? Susceptibility of steel to get hardened, open, quenching, and it basically tells us the depth and distribution of hardness across the cross section. Across the cross section means from the surface to the center, or from the surface of the steel to the core of the steel, what is the depth and distribution of hardness, right? Similarly, in other definition, we can say like this: hardenability is the ability of a steel to get hardened by forming martensite throughout the cross section of the steel without drastic or very rapid cooling. So this is the definition of hardenability. So in simple way, I can define hardenability is nothing but how easily we can form martensite throughout the cross section of the steel. You understand? Because the cooling rate, if the specimen of the steel is very thicker, or it is of very big dimension, then what happens? The surface cooling rate will be higher and the center cooling rate will be lower. So due to different in the cooling rate at the surface and at the center, or there is a gradient in the cooling rate starting from the surface to the center of the steel, we can get different microstructures, right? When the cooling rate is very high, maximum chance we will get martensitic microstructure. When cooling rate will be slow, maximum chance that we'll get perlitic microstructure, right? So obviously, due to difference in the microstructure, we will have different hardness at different cross section of the steel, right? So that is the concept of hardenability. So many people get confused in this term, hardness and hardenability. So hardness and hardenability are not same. They're different actually. If you remember the definition, already you understand the hardenability definition. If you remember the hardness definition, it is nothing but what? Hardness is the resistance to plastic deformation, which can be measured by indentation method. By indenting a ball or a square pyramid base diamond, like that. A steel ball, something like that. So with the help of this graph, that is hardness versus distance. Hardness versus distance, you can able to understand this one. So you can see this part is surface and this part is the center. So you understand, you have a piece of steel. Suppose you have a piece of steel which is of like cuboid shape piece of steel, right? This part is showing you the center part of the steel, and this part is showing you the surface. So that means from the surface you are going to the center like this. So what will be the hardness? So you can see the graph is this one. Okay? So that means at the surface the hardness will be maximum, and if you are going into the center and you are measuring the hardness is falling down. It is getting decreased to the center. So suppose you want to show the hardness of the other surface, because surface, suppose you, this is the top surface, you want to see the hardness of the bottom surface. So you have to extend this graph and you have to write this surface and you have to extend the hardness. So what will the graph will be like this. It will increase. It will go like this and again it will increase and reach to the surface. So this is the depth and distribution of hardness. Hardness is maximum at the surface and minimum at the center or the core of the steel. And this is because of difference in the cooling rate, and due to difference in the cooling rate we have different microstructure. And martensitic microstructure is very harder, perlite microstructure is somewhat softer as compared to the martensite, right? Now this is a very interesting graph you can see. So again you have, this one is showing you the hardness. This part, this y-axis is showing you the hardness, and this x-axis is showing you the distance. So this is the center of the steel. This is the center or the core of the steel. And suppose you are moving in this direction, and also you are moving in this direction from the center. So this is the center of the steel. From the center you are moving in this direction. Suppose this is the surface. Surface is, suppose this is the top surface, and this surface is the bottom surface, right? And this is the center of the steel. And this y-axis is the hardness value. So I have two type of steel here. We have steel A. So this is the curve for the steel A, hardness curve, and this is the steel B, hardness curve for the steel B is like this. So can you people tell me, by looking at this graph, what is the, which steel is having maximum hardness? Steel A or steel B? Let me see who can answer. I'll give you 10 seconds to think of it. Your time start now. Just think and tell me which steel will be having high hardness. Or what is the relationship between hardness of A with the hardness of B? Which one will be greater, which one will be smaller, or are they same?
Sir, B has more hardness.
B has
More hardness.
more hardness. Anybody want to try? Some you have answered something. You have 3 seconds more. Okay, time's up. So Soumya is right. You can see the steel B is more harder. So hardness of steel B is greater than hardness of steel A, because you can understand this is the hardness value. This part is the hardness value, and we measure the hardness from at the surface only, right? Surface of the steel. So you understand basically the hardness is maximum because it's starting from this higher value, right? Here it is also at the surface is at higher value, but hardness of steel A is lower. So hardness of B is greater than hardness of A, right? So can you people tell me what about the hardenability? Hardenability of A and B are same or different? If same, how? If different, how? What is the relation? So again, you have 10 seconds to think of it.
So different.
Hardenability will be different. Okay, if it will be different, then which one will be have good hardenability or high hardenability, and which one will have poor hardenability?
Sir, steel A has good hardenability.
Steel A has good hardenability. Okay, can anybody tell me anything? Anybody want to speak something else? Can anyone want to comment on this? Yes, your time is over. Yes, so Somay is again right. So steel A have high hardenability or good hardenability as compared to steel B. How it can be justified? It can be justified by looking at this curve only. You can see the hardness from the surface and the center is not varying much. There is no more changes in the hardness value. You can see they are nearly comparable hardness. Hardness at the surface of the steel for the A at the surface and at the center or at the core is nearly same. It is not so much difference in the hardness value for the steel A. But if you look at the steel B, you can see the hardness at the surface is very high. But if you go down to the center, either from the bottom surface or from the top surface, you can see there is a huge difference in the hardness value at the core or at the center. So center hardness is very less, but surface hardness is very high for the steel B. But in case of steel A, the hardness at the center and the surface is nearly same or comparable, right? So that's why steel A is having good hardenability or high hardenability as compared to steel B. But if you compare the hardness value, then steel B have high hardness as compared to that of the steel A.
Hello, sir.
Yes.
Can you repeat what is the definition of hardenability?
Hardenability is the ability of a steel to get hardened by forming martensite throughout the cross section, right? Without drastic quenching or without very rapid cooling, or
Uh,
it denotes or it signifies basically the depth and distribution of hardness throughout the cross section of the steel, or it is susceptibility of steel to get hardened upon quenching. Yes, Devi Prasad, you want to ask anything else?
yeah, one more question that the steels A and steel B, these
Yes.
are already it is like this or some treatments they are undergone? Because I'm asking because from the
Yes.
standard, if
Mhm.
after some treatment, steel A is not much showing any deviation, but still if steel B is showing deviation like this, then
Yes.
hardenability should of B should be very more, I think, like that.
Hardenability of steel B will be more, you are saying.
Yes, sir.
Okay. But do you understand the definition what I told?
Means yes, I understood.
Yes.
But
The point is what we want martensite to be there at the surface of the steel and at the center or at the core of the steel, right? Everywhere we want a martensite. But if we want a martensite, we understand we should reach to the critical cooling rate, or the cooling rate should be higher than the critical cooling rate to get martensite. But the problem is what? Due to the dimension of the steel or due to the thickness of the steel, the surface, the cooling rate is somewhat higher, but at the core, the cooling rate is somewhat lower. So if the cooling rate will be different, and if the cooling rate is higher at the surface, martensite will form at the surface or just near to the surface, martensite will form. But if you go depth into the core or at the center, perlite will form, because cooling rate is slow, diffusion will happen, and perlite formation will be there. That means austenite will decompose into perlite. But at the surface, due to high cooling rate, the austenite will decompose into martensite, right? The hardness value we are measuring means we are measuring the hardness of the different phases, right? At the surface, it is martensite, so it will give you high hardness value. And if you go into the depth, into the core, you'll get perlite. The perlite hardness value will be less. You understand? Devi Prasad?
Yes, sir. Yes.
You understand the point right now?
Yes, sir.
So that means in the steel A, it has high hardenability because why? Because the depth of hardness is nearly comparable or nearly close at the surface as well as the core. That means here martensite has formed, here also martensite has formed. Here has martensite has formed. So martensite is forming everywhere. At the surface also, at the center also. But in the steel B, what is happening? You can see at the surface hardness is maximum. That means martensite is forming up to a depth of this much, or up to a depth of this much, or up to a depth of this much. But below this one, this is perlite, right? Again, at this surface, it is martensite, right? So as I told, hardenability means how easily the steel is forming martensite, but that martensite should form everywhere throughout the cross section of the steel. It is not like that martensite will form at the surface only. It will not form at the core or at the center. I think your doubt is clear right now.
Yes, sir.
Yes. But if you compare the hardness value, obviously the hardness value is higher. It is clearly showing. Hardness value of B, steel B is higher than steel A. Okay. Now, the concept of maximum hardness value in plain carbon steel and how to achieve that. So this is a very interesting question. So I'll give you 5 seconds to think of it. Suppose you have a plain carbon steel, how you can get maximum hardness then? You can tell me in terms of microstructure, you can tell me in terms of composition. You have 3 seconds more.
कार्बन आड करी करी गले हार्नेस
Sorry, can you repeat? Yes, can you repeat? Martensite. Someone is saying. Yes, Latmika, you are right. Absolutely right. Because you understand martensite is a very hard and brittle phase, or it is a very harder phase. So you can have maximum hardness value. That is on in terms of your microstructure. In terms of composition, or I can write complete martensite. The answer is very simple. Chemical composition. Tell me. What is the relationship between carbon weight percentage and hardness value?
हेलो सर
Yes. Yes,
तो
Soumya.
जब हमें कार्बन ऐड करी करी जिबा अप टू सीमेंटाइट जदी हेबा तांता हार्डनेस तार अधिक है
Yes. If cementite will form, the hardness will be more. So what you want to say actually? Tell it clearly. Yes.
सर कार्बन ऐड करियो
Okay, fine. Very good. Chemical composition means more carbon weight percentage. So these are the basic things you understand chemical. That means more is the weight percentage of carbon, more is the hardness value of the plain carbon steel, and more is the that means if only martensite will be there, that is a very hard phase, right? You can have cementite also if some cementite phase is forming, so it will also provide you some hardness value, right? But since we are not talking about this cementite, we are talking about martensite, and we are talking about this carbon weight percentage, since we are dealing with plain carbon steel. So this is enough to get maximum hardness. So now the question is how to achieve this. How to achieve this? How to achieve this maximum hardness? The answers are very simple. The first thing what you have to do, is
Quenching.
quenching. Yes, quenching. But before quenching, that is something important. Before quenching, you should need to do something.
Homogenization of austenite.
Homogenization of austenite phase. Very good. Homogenization of austenite phase. Okay. So I can write all carbon must be in soluble form in austenite, right? But homogenization, all the carbon must be in soluble form in austenite. That is very good. Next step is, as he told, quenching we will do, so that we'll get martensite. But that is fine. But you should write no retained austenite must be there. It is okay now? You understand? If austenite, retained austenite will be there, what will happen to the hardness? If retained austenite will be there, what will happen to the hardness value of the steel?
Hardness value is decreased.
Very good. It will decrease because austenite is a soft phase or a tight phase. Only martensite. Fine. Anything else? One is all carbon must be in soluble form in the austenite phase. Second one, no retained austenite must be present. Upon cooling from the austenite region, only martensite should be there. This is the second part. Anything else? Achha, how to get 100% martensite? By obtaining?
Quenching.
By obtaining which kind of cooling rate? Critical cooling rate is achieved, right? Must be achieved during cooling. How many of you remember what is critical cooling rate?
Sir, just above the nose.
Just above the nose, or it should just touch the nose?
Sir, I'm not sure.
You are not sure. Okay. Anybody want to speak something about this?
Cooling curve should just touch the nose of C
Yes,
curve.
very good. It should just touch the nose of the C curve, right? Just it will touch means there is no transformation. Basically, you can understand. Only the austenite will transform into martensite. But if just it will cross, then some transformation will start. Like it may transform into some perlite also, right? So that is the thing. Just you can understand. Critical cooling rate is that cooling rate which will just touch the nose of the C curve of TTT diagram, right? Or of the CCT diagram. Anything is fine, and it should. And the point is, it is just like a tangent. The cooling, that critical cooling rate curve is just like a tangent to the nose of the C curve, right? So if you want to form martensite, the cooling rate should be higher than critical cooling rate, or it is critical cooling rate, that is also fine. Anything else? And the interesting point is there should be no auto tampering. No auto tampering of martensite. How many of you remember what happens if tampering occurs? And due to which, or due to what thing, what happens? How many of you remember the auto tampering process? What happens during tampering? Yes.
Diffusion.
Can you repeat?
Diffusion occurs in tempering.
My question was, what happens during tempering process? How
Ductility
many of you
increases,
remember
brittleness decreases.
ductility increases? Okay. So only ductility increases?
So toughness increases.
Toughness also increases. Very good. And what decreases?
Brittleness.
Brittleness decreases. Okay. What happened to the strength and hardness value?
So they decrease to some extent, but still it's good.
Okay, fine. Yes. The hardness and strength also decreases. But ductility and toughness increases. Hardness and ductility increases somewhat in the steel. So, okay, why this happens? How many of you remember? And who remember tempering is followed by which heat treatment? Or tempering is an independent heat treatment, or it is always followed by certain heat treatment?
Followed by hardening.
Very good. Tempering is always followed by hardening. Very good. So, how many of you remember what happens in the tempering so that the ductility is increasing, some toughness is coming into the picture, but hardness and strength is decreasing to a particular limit? But it is good, as Soumya told. Fine.
So diffusion.
Very good. Diffusion starts at tempering process, right? During tempering, we are again rising the temperature of the steel and diffusion starts. So what happens if diffusion starts?
So carbon will come out of
Martensite. Very good. Carbon will come out from the martensite. So martensite, if the amount of carbon in martensite is very high, it is more harder and stronger, right? Or it is brittle one, right? Because the tetragonality is increasing, right? But if you decrease the amount of carbon, the tetragonality of the martensite will decrease because the carbon is ejecting out from the martensite, because martensite is a supersaturated solid solution of carbon here, basically. So if you rise the temperature, diffusion process starts, the carbon will eject out from the martensite, so tetragonality of the martensite will decrease, the hardness and the strength will decrease, basically. And if you do tempering for a lot of time, so a lot of carbon will come out. Finally, you will end up with the ferrite matrix with cementite precipitates, or this spherical shaped cementite precipitate. Ferrite matrix means it is very soft, tougher. And you understand some intermediate carbides form, like epsilon carbide, Fe2.4C, right? During this process. And some recovery is also taking place. And your carbon is moving to the dislocation sites, or any defects will be there. So these are the things happens during the tempering process. Anyways, so you people have understood, if we want maximum hardness in the plain carbon steel, we should have 100% martensitic microstructure, and we should have what? More carbon weight percentage in the plain carbon steel, right? Because higher is the weight percentage of carbon, higher is the hardness. And this can be achieved by these things. There should not be no auto tempering. If auto tempering will be there, then hardness will reduce, right? There should not be any written austenite. If written austenite will be there, written austenite is a soft and ductile phase, so the hardness will decrease, right? And we can, during the cooling from the austenitizing temperature, the cooling rate should be critical cooling rate, or it should be higher than critical cooling rate, so that we can have a martensitic microstructure. And another point is, all carbons should be remain in solution form in the austenite phase, right? So these are the points. Now, condition affecting the hardenability. So this part we will not discuss in depth. In some point of time during your next lecture, we'll discuss this one. So here I'll tell you an overview of this. The conditions affecting hardenability of the steel. So what are the conditions that will affect the hardenability? The first condition is obviously the austenite grain size. Second condition is alloying element, presence of alloying element. Third thing is dimension of the steel. Anything else? Coolant used for quenching. Coolant used for quenching. Right? So these are the different conditions which will affect the hardenability of the steel, basically. But right now, I'll tell you one important point here, just an overview. Austenite grain size should be higher to get high hardenability in the steel. You should remember. And presence of alloying element means if more alloying element will be there, more hardenability will be achieved easily. And dimension of steel, you understand, dimension of steel should be minimum, right? The thickness of the steel should be less so that we can get everywhere martensitic microstructure. And coolant means the strength of the coolant. It is very strong coolant or weak coolant, or that means strong and weak coolant means the rate of cooling by using a suitable coolant, you can achieve this critical cooling rate. So that is the part. So these are the things. Next is how to get martensite at the core center of the specimen, and what is the consequence of this. So the answer is we can get martensite. We can get martensite at the core or at the center of the steel by doing drastic cooling or quenching, right? Because if we do drastic quenching or cooling, the cooling rate will be become the critical cooling rate at the center. Because the only point is, if we want martensite in our steel, the cooling rate should be critical cooling rate, or it should be upper critical cooling rate, in other words you can say, or cooling rate should be greater than critical cooling rate, right? To get, I am writing, to get martensite in steel, the cooling rate should be critical cooling rate or upper critical cooling rate upper critical cooling rate, or I can write cooling rate must be higher than critical cooling rate. Can you people tell me if the cooling rate will be critical cooling rate, and if the cooling rate is very higher than critical cooling rate, which one is suitable?
Sir, actually critical cooling rate is good, but for maximum hardness we can go to high.
Okay, fine. If you talk about the properties of the steel, which one is good?
Critical cooling rate.
Yes, very good. Why?
Sir, because their brittleness is lowest. Means
Yes, very good. So that means more strain will be there in the structure if the cooling rate will be very high. The question was consequence of this. So consequence of drastic cooling is what? Warping of steel may occur, and the thing is crack may occur. Cracking of steel may occur. So you people have understood now. Okay. Warping means twisting, basically, or there is like bent in the steel specimen, right? The cooling rate is, if somewhat very higher, the steel may bend during the quenching or during the cooling, or it may get twist, kind of thing. or cracking means crack formation will be there, like quench crack. Okay, next is steel types on the basis of hardenability. So we can classify the steel on the basis of hardenability concept. So we have two types of steel on the basis of hardenability. One is that is, you can call it shallow hardenable, shallow hardening, HARD, shallow hardening steel. So another one is deep hardening. So two types of steels we have: shallow hardening steel, deep hardening. The name itself is saying, right? What is shallow hardening? Shallow hardening means the hardness value is not so high at the center. Deep hardening means the hardness value is more towards center also, right? Or shallow hardening, in other words, I can say depth of hardness is limited. Depth of hardness is limited. To a small distance. So depth of the hardness is limited to a small distance from the surface, right? But here uniform hardness. Uniform hardness throughout the cross section. Throughout the cross section. Hardness throughout the cross section. Uniform hardness throughout the cross section, right? So deep hardening steel means that is actually property of that steel. That is the nature of that steel. That means it will automatically form martensite throughout the cross section, right? Or I can write it forms martensite everywhere. But it forms martensite close to the near to the surface only. Right? That's why it is shallow hardening. Example is obviously plain carbon steel. Plain carbon steels are shallow hardening, right? But these are alloy steels. Alloy steels are deep hardening steels. That means if you have a deep hardenable steel, it will become hardened everywhere, because everywhere martensite is forming. Okay, if you measure the hardness starting from the surface to the center, it will be nearly uniform. But in case of shallow hardenable, the hardness will be maximum at the surface, but minimum at the core or at the center. Now, ways to distinguish perlite martensitic microstructure in steel. So how you can distinguish perlite and martensite microstructure in steel? So already you have attended the IPM class. Can you tell me IPM and your introduction to physical metallurgy lab class also? So how you can distinguish perlite and martensite? What is the mechanism? By? Tell me quickly. By? What is the answer? By?
Microscope.
Microstructure analysis. Very good. By looking at the microstructure. So perlite will appear as which kind of, and martensite will appear as which kind of thing? By optical microscope, how it will appear. Perlite appear as a lamellar structure, right? But martensite will appear as like of needle shapes, but it's not exactly needle, it is plate. But in my optical microscope, it appears as a needle shape kind of thing. Okay, by looking at the microstructure. Anything else? How you can identify? By fractography. By fractography, analysis. Fractography means? Fractography means it is a study of fracture surface. Can you people tell me how many type of fracture we have in the material? How many type of fracture occurs in a material?
Sir, three types:
Yes, what are they?
ductile, brittle, mixed.
Okay, how the fracture surface of a ductile surface looks like? Have you seen? Have you people seen the surface of a fracture surface? Surface of a fracture materials surface? Have you ever seen? Okay, basically the ductile fracture looks like dimples, like it will appear as a dimples. Dimples means it will be having some voids like that. And brittle fracture is completely like facets. It's like complete a face, plain face, a sharp face will be there, right? But in case of ductile fracture, you will have some voids. Lot of voids will be there. It will like looking like a dimples in your face. So study of fracture surfaces, you can write perlite fractures in ductile way. But martensite fail with or fracture with fracture with brittle, right? Because martensite is a hard and brittle phase, so it will show brittle fracture surface, and perlite will show ductile fracture surface. So you can easily distinguish them, right? So in perlite, you will be having dimples. So in where there is martensite, it will be having facets basically. This fractography study is done with the help of SEM, scanning electron microscope, right? This is an electron microscope. And next thing is you can measure by measuring what? Hardness value also. By measuring hardness value, because surface obviously the hardness will be more because martensite will be there. And the point you are measuring the hardness by measuring the hardness value across the cross section. That's the depth otherwise of the steel. So where you find there is a decreasing in the hardness, there is a sharp decreasing in the hardness, you understand there is the perlite is present. Where there is high hardness value, it is martensite is present, right? So these are the ways. I'm measuring the hardness across the cross section or across or into the depth. You can have study of fracture surface by using scanning electron microscope. You can see different type of fracture surface, ductile and brittle, and you can look at the microstructure simply. Perlite will appear as lamellar structure and martensite will appear as a needle shape kind of thing, not clear structure. It will show the significance of hardenability. So this is very simple. The property tells us the maximum hardness achieved by the large cross-sectional steel at its surface upon drastic quenching. That means you have a very thicker cross-section material and you are doing drastic quenching, means very fast rate of cooling. So how much maximum hardness you can get at the surface is that is the significance of hardenability. And the one is it determines the rate at which given steel should quench, right? Now hardness versus transformation temperature. Transformation temperature means transformation of austenite to different product. So what is the relation? Can you people tell me quickly? Let me see who can answer. This is a very simple question. Hardness versus transformation temperature. How they are related?
Sir, inversely.
Inversely related. Very good. So lower is the transformation temperature, higher is the hardness. So what is the justification to that?
The lower is the transformation temperature, the liquid will be the quenching, and that's why
Liquid will be the
hardness.
quenching, or the structure often will be non-equilibrium microstructure.
Yes, sir. The non-equilibrium microstructure is up.
Yes, that is the answer. Higher is the transformation temperature, equilibrium microstructure will obtain. Lower is the transformation temperature, non-equilibrium microstructure will form. Like benite and martensite will form, that is non-equilibrium microstructure. But higher is the transformation temperature, equilibrium microstructure will form, like perlite will form. So obviously, hardness and transformation temperature are inversely related. So next is how to achieve better property in steel on the basis of transformation temperature. Who can answer this one? Let me see. How to achieve better property in steel on the basis of transformation temperature. Better property means good hardness, good strength, good toughness, like that.
Sir, it should not be very low, but a optimum level should be there.
The answer is very simple. To obtain better property in steel, right? The transformation should not happen at high temperature, because if transformation happens at high temperature, then perlite will form. So we try to avoid this always. So to achieve better property in steel, the transformation should happen at the very low temperature, because we can obtain either benite, that is lower benite we can obtain, or we can obtain martensite. So if you are obtaining martensite, that can be again tempered to get better property. Combination of good strength, good ductility, good toughness, and good hardness also, right? So this is the answer. Now cooling curves superimposed on CCT curve and microstructure obtained. So this is a very interesting part. In the previous lecture, we have discussed about the continuous cooling transformation, where we have seen that the continuous cooling transformation curve is basically moving downward and shifting towards right somewhat compared to that of TTT diagram, right? And also we have seen in the continuous cooling curve, the curve is up to the nose of the TTT curve. It is not below that. It is absent, right? So now we can see these are the cooling curves. This is the one cooling curve. This is the next cooling curve. This is the next cooling curve. And this is the next cooling curve. You can see cooling curve starts from the temperature above the eutectoid temperature. That means here austenite is present. Homogeneous austenite is present. And upon cooling, what is the transformation? So you can see the first cooling curve is like this. So it is forming fine perlite. Can anybody tell me why it is forming fine perlite? If the cooling rate is like this, why it should form fine perlite? What is the justification to it? First, tell me why it will form perlite. The second question is why it is fine perlite. Let me see how many of you can answer. Soumya, don't answer. I don't want answer from you, Soumya Panda. I want answer from others. Jnanananda, can you answer this one? Why this cooling rate, or why this cooling curve is producing fine perlite? First question is why it will form perlite, tell me. Next, why it is fine perlite, why it is not coarse perlite. Jnanananda? Jnanananda, you are there?
Yes, sir. Hello.
Yeah, just answer the question.
Don't know, sir.
Okay, fine. Jyotirekha, can you answer this one? Jyotirekha? Jyotireka, you are absent? Okay, fine. You are absent. Sagar Sahu?
Yes, sir.
Sagar, can you answer why this cooling curve is showing it is producing fine perlite? The first question is why it will form perlite and why it is fine, not coarse. This cooling rate.
So don't know, sir.
Okay, you don't know. Siva Prasad, can you answer this one?
सर स्लो रेट ऑफ कूलिंग हो जो ऊपर सर से जो
Okay, slow rate of cooling. Okay, fine. But tell me in terms of, I want to correlate this cooling curve with the CCT. This is the CCT part? CCT curve?
Yes, sir.
So can you please correlate on that basis?
सर हाई टेम्परेचर भी होची ना सर से कर्वटा हाई टेम्परेचर आछी जेतु सर ट्रांसफॉर्मेशन स्टार्ट आउ एंड रे डिफ्यूजन होची तेनु परलाइट आछी
Okay, yes. Okay. Your answer is not clear, but I think you understood the point anyways. Swapna Mai, can you answer? Yes, you can leave. Swapna Mai,
Yes, sir.
can you justify why this cooling rate or this cooling curve is forming fine perlite?
Sir, less holding time.
Less holding time, dear, we are cooling the sample in a continuous way. So holding time will not come. No? Holding time depends upon the starting conditions. But here we are cooling and we are cooling continuously.
Sir, fast rate of cooling.
Fast rate of cooling will form fine perlite.
No, sir, Martin.
Yes. So I want answers by correlate this one. What is this curve and what is this curve? And this is the cooling curve. So I have given you enough hint right now. Okay, anyways. Sonalata, can you answer this one? Can you answer this one or yes or no?
No, sir.
No. Shweta, can you answer this one?
Yes, sir.
I can right now I can see only
Hello?
36 number of students here. Shweta, can you answer that one?
Yes, sir.
Yes.
Sir, normalizing होची सेतिपाई fine होबो.
No. My question was, you have to justify with the help of this CCT diagram curve with this cooling curve. If you can correlate, then you can easily tell me the answer. Let me give you a hint. This is what is this curve is showing and what is this curve is showing, and this curve is like moving like this.
Sir.
Okay. Amrita? Amrita, can you answer? Aditya Acharya, can you answer?
PCD curve dita curve को touch करछो.
Yes, it is touching two curves. Okay. So can you elaborate this one? If it will touch two curves, then?
No, sir.
Okay, fine. Okay, Jibojyoti?
Yes, sir.
Yeah, can you justify?
Sir, I think we are having a perlite bay in the curve that's why the cooling curve is touching that.
See. Wait. Just hold on. Perlite bay is here. It is benitic bay. It is perlitic bay basically. But why you are talking about those bay?
Sorry, sir.
Yes. Okay. Anyways, Pratiksha or Pritisika, anybody want to speak? Or Rameshwari?
So,
Sir, first one is the transformation start
Very good.
temperature, and second
Very
one is
good.
transformation end temperature,
Very good.
and
Very good.
there is more gap between them, so that
Yes.
it is slow cooling.
Okay. Anyways, Rameshwari is not exactly right, but she's saying somewhat right thing. Okay. Can anybody want to complete this one? Layatmika, can you answer?
sir, I think the cooling rate is above upper critical cooling rate.
Okay, that is one part. But I want justification on the basis of this one, this curve and this curve. You have already attended the TTT curve diagram. You have already attended the CCT curve diagram. How transformation starts and how transformation ends. Already you know those things. Okay, anyways, let me explain. See, the cooling curve is moving like this and it is touching the curve 1 and again it is touching the curve 2. Listen it carefully. This cooling curve is starting from here, but it is touching this one and it is also touching the this. So this curve is nothing but the transformation start curve, right? So that means the moment it is cooling like this and it is touching this one, so austenite will transform into perlite, right? But transformation is not finished. But again it is moving and it is touching the transformation end curve or finish curve. So that means what happens after this point, all the austenite has transformed into perlite. Why? Because this is CCT curve and this is up to the perlitic curve, right? Perlitic region. It is not below the perlitic region. I think you people have understood right now why this will form and why fine perlite, because cooling rate is somewhat faster. If the cooling curve will be like this, then it will form coarse perlite. But if the cooling curve is like this, it is forming fine perlite because cooling rate is somewhat higher. And why perlite is forming? Because this curve is touching the transformation start curve and also transformation finish curve. I think you people have understood right now. If you have any problem, you can ask me right here. It is okay?
Yes, sir.
Similarly, can anybody right now justify why this cooling curve is giving rise to perlite and martensite both? Let me see who can answer. Why this cooling curve? Anybody can answer, huh? If you have understood, can you tell me why this cooling curve is showing you formation of perlite and martensite both? This one.
So because the curve is exceeding that M
Yes.
F.
Exceeding that M, S, and F. But this curve is also exceeding.
Only exceeding the MS curves. So that's why only fine perlite is present.
No,
And
no.
here,
My question is why this curve is showing formation of perlite and martensite. Both microstructure will be there in the steel. Perlite will be there, martensite will be there. And you are saying this curve is also touching the MS and MF.
yes. No, sir. It is crossing only MS. And
No. It is crossing MS means martensite will be there now, obviously. But it is only fine perlite. Okay, I will extend the curve up to this. Okay, I will extend the curve up to this. So, yeah, somebody is saying, yeah.
Sir, because the curve don't touches the transformation end line.
Very good. It is not touching the transformation end line. So that is one part. Yeah, can you elaborate that one again?
Sir,
Yeah, that is not.
because
Yes.
sir, as the curve don't touches the transformation end line, but it crosses the transformation start curve.
Very good. Very good. Yes. Yes.
So,
Then
some austenite transforms to perlite, but there is still some austenite unstable present.
very good.
And
Very good.
when it touches the martensitic start temperature, that
Yes.
austenite transforms to martensite. And
Swami, excellent. Yeah, I am really happy with your answer. That is the answer only. You can see that this cooling curve is moving like this, and it is touching and crossing the first curve. And this first curve is the transformation start curve. That means some transformation has started only. That means some austenite is transformed into perlite, right? But it is crossing this line. That means it is not touching this line. This line is the finish line. So since it is not touching this line, that means some austenite has transformed into perlite, but some austenite is still there. So since cooling curve is moving like this and it is touching MS and MF. So that means what will happen? Rest of the austenite will transform into martensite, right? So some of the austenite has transformed into perlite, and rest of the austenite has transformed into martensite because this cooling curve is touching MS and MF. But if you might have a question like, this curve is also touching MS, but why martensite is not formed? Because already you can see this cooling curve had touched this first curve and second curve. That means all the austenite has transformed into perlite. No austenite is remain now. So that is why there will be no transformation of to martensite. Only perlite will be there, right? If you want to form martensite, then perlite transformation must be suppressed. It is okay. I think you people have understood right now.
Yes,
if
sir.
you have any confusion, you can ask me right here. Okay, fine. So can you people tell me what is this cooling curve name? What is the name of this cooling curve? Just look at this one. Or what is the rate of cooling?
Critical cooling.
Critical cooling rate. What is the meaning of critical cooling rate?
The cooling curve is just tangent to CCT curve.
Very good. CCT curve or TTD curve, anything. Or nose of the nose. You should mention nose. Nose of the TTD curve, or it is just tangent to the nose of the CCT curve, right? Very good. So product will be what? What is the product?
Martensite.
Martensite, right? And can you people tell me what is this cooling rate? What kind of cooling rate is this? Or what is the cooling curve of this is showing? This cooling rate is very higher as compared to that of the critical cooling rate. So what is the product? What will be the product here? If the cooling rate is this much?
Martensite.
Martensite. Because cooling rate is higher than that of the critical cooling rate. Okay, I think you people have understood very well. So this is the last part we will discuss in the today's lecture. That is hardness value at different depth in HRC. How many of you remember what is HRC?
Hello.
How many of you?
Sir.
Yes.
Sir, ଏବେ lunch break ଟା sir आपरे खाଇବା ସରିଯିବ ତାପରେ sir ଅଢେଇଟା class ବି ଅଛି lab ଅଛି ma'am
I will take only 2 minutes to explain this one. Just tell me what is the meaning of HRC.
Hardness Rockwell C.
Rockwell hard, yes, very good. Rockwell hardness scale, very good. Anything. So you can see this is the hardness value. In this axis I am showing hardness, and this is showing the distance from the center. So this is the center, it is moving toward the surface. This is the center, it is moving toward the surface. So you can see the hardness value. The hardness curve is like this. So that means maximum hardness is at the surface, minimum hardness is at the core or at the center. So what is the value here? You can see 65 RC, and at this point it is 54 RC, and at this point it is 40 RC. So that means if the hardness value is 65 RC or Rockwell hardness scale 65, it means we have 100% martensitic microstructure, right? Because few minutes before we have discussed a slide where I have mentioned how to distinguish martensite and perlite, right? So if the hardness value is 65 Rockwell hardness scale, then it is 100% martensitic microstructure. If it is 54, then it is 50% martensite and 50% perlite. If it is 40, then it is 100% perlite. So you have to remember these figures: 65, 54, and 40. I think you people have understood right now. Okay, I will end the topic here. If you have any doubt, you can call me or you can text me.